that's one of the theorems that you can prove. It's a very nice theorem that you can prove using Grosvenor basis. So I hope that gives you some idea of why it is that we really want to study these guys. But there's a more concrete question, which is, okay, do these things exist? I just gave you a definition, but I still haven't shown you the first example of a Grosvenor basis. Right? So far, I showed you an example of not a Grosvenor basis. Yesterday we saw something that wasn't. But I don't want to create too much suspense here. So these things do exist for any ideal and any polynomial order. So this is good to know. You can always find it. Given that we know that, other answer to the questions there are, how do you recognize a Grosvenor basis? So last time we showed that two polynomials were not a Grosvenor basis, and it was kind of a what I would call an ad hoc argument, meaning that I just kind of came up with a polynomial that showed that they weren't. But how do you do that systematically? And a very natural question is, if I'm telling you that Grosvenor bases always exist, then how are you going to find it? So very natural, like, algorithmic question that we will discuss. So the first thing I want to talk about today is an application, which is this one. So suppose that you have a Grosvenor basis, and what we want to know is, we want to test, this is called the ideal membership problem. I give you an ideal, I give you a polynomial, and I ask you, is that polynomial a member of the ideal? Okay. So we will focus on that. Testing ideal membership. And well, generally, the way that we are given an ideal is by a set of generators. So we can think of this ideal as being given by the generators G1 up to Gk. So think about how we do this. For example, for a single polynomial, and let's say for a single variable. Okay, so this is a question that takes place in several variables, but let's talk about a case that we're familiar with. If I give you a polynomial in one variable, and I ask you, is this in the ideal generated by another polynomial in one variable, then what you do is, if you want to know if f is generated by g, you just divide f by g, you use long division and see if that works. And this is kind of what we have in mind here, is we're going to do long division of f by all these polynomials. This is something called the division method. So the input is f and g1, g2, and gk. And the goal is to write f in terms of these guys if you can. Okay. But as you can imagine, you can't always do this, and sometimes you're going to have a remainder. Okay. Now, what does it mean to be a remainder? This is a little bit tricky now, because for polynomials, you know you have a remainder when the setup we're used to is this one. Let's say that we do it in just one variable, and with only one g. What long division does is that it keeps dividing until it gets a remainder whose degree is smaller than the degree of the dividend. So, degree of r is less than degree of g. That's when you stop. Okay? But if you see that, then it's not so clear when we're supposed to stop here, because, well, first of all, what does it mean for degree of r to be less than degree of g in several variables? Well, we're going to need a monomial order to decide that, first of all. But second of all, which one of the g's should you compare it? Well, it turns out that what we're going to want is first of all, I'll tell you the second condition, which is that R is minimal in the sense that I cannot divide it any further. And what I mean by that is that none of the monomials in R are multiples of any of the leading monomials of the g's. So no monomial of R is a multiple of the initial polynomial of any g. We'll see this in an example, and I think it'll be clear why I'm doing this. And the other condition is kind of clear, which is that the initial term of f should be greater than or equal to the initial term of all of these guys. Okay. But you see here, this greater than or equal one sign depends on what we mean by this. We need a monomial order to this. Okay. And that's not up to us. So we should also be given a monomial order to decide this. So that's what we're at. And so I'm going to give you an algorithm for doing this. But maybe when we do this algorithm, we'll keep in mind a very specific example. Two variables. Let's say that this is my polynomial f, and g1 is xy plus 1, g2 is x plus y, and the order is lexicographic with x less than 1. So that's the input. And so what I need to do is that I need to give back an expression of the form this is equal to some polynomial here times xy plus 1 plus some polynomial here times x plus y plus some polynomial that's going to be my remainder. That's the plan. Okay. So let's go ahead and do this. So let me tell you how we're going to initialize the algorithm. What we're going to do is that we're going to first let these guys be 0, 0, and 0. Okay. But I know you don't want me to stop there because this is not an equation, right? So I'm going to need an error term. So I'm just going to put it over here. So let me say that I start with setting all of these QIs to be equal to 0. I'm going to let R equal to 0, and then I'm going to introduce an error term that in my notes I call S. I guess I should tell you that this is in my notes according to today, but if you look at the notes in the website, I didn't have S in there. So I'll post it. I'll repost these. Okay. But this is what you should be thinking of as S are Q2 and then the plan is going to be very similar to how we do the usual long division. The point is that I want to just kind of peel things off of S and put them into the Q's and the R. Okay? How am I going to do this? Well, what I'm going to do is I'm going to do this according to the leading terms. Okay? So, for example, this is the leading term of S. And that's the guy that I'm going to try to distribute. And let me just underline the leading terms of G1 and G2 also. Sorry?
Yeah, I'm confused. I thought that the X was bigger than Y, but X was
Oh, sorry. That is what I meant.
Okay.
So X, X, Y goes before Y in the dictionary. And so I'm going to do this. So, right, so what I said is peel things off of S and into the QIs and B. So what I do is this. I say, and I always do that by canceling out the biggest term, which is exactly what we do in our division. Okay? So I say, I want to cancel that X squared Y. And so I'm going to use, for example, this guy to cancel that X squared Y. And how do I do that? Well, what I need to do is put an X here. Okay? If I do that, then I'm going to lose this X squared Y. So I'll leave this guy alone. I'll leave this guy alone. And now, this X squared Y already went over there. And now what I'm going to get is a minus X that this guy falls back into here. Okay? And so that's an equation now. So what did I do here? What I did is that I said, I took the initial term of S, and that's my term X squared Y. And I tried to see if it was a multiple of one of these initial terms, which it is. So let's say that it's a multiple of the initial term of, get rid of all these less than because I said it. So the initial term of S is something times the initial term of one of the GIs. I call this MI, in this case MI is equal to X. Then what I do is that I take that away from S. So I had S and now I just subtract MI GI. Okay. And my quotient QI, I'm going to add MI to it. And so that's exactly what I did here. I said I look at the initial term, it's X squared Y. I see if it's a multiple of this guy or this guy. And I say, okay, well X squared Y is a multiple of XY. And the factor that I need is X. And so I add X to Q1. But to keep this equation true, I have to subtract this to S. And now S becomes something different. And I repeat. Okay. I repeat, but in order to repeat, I have to again figure out what the leading term is here. The leading term is this one. And I have to see if this guy is a multiple of this one or of this one. Okay. Well, it's not a multiple of this, but it is a multiple of this. And so what I do is I keep this guy alone, and then I add here whatever I need to cancel this minus X. And so that's a minus 1 X plus Y. Keep this at 0. And to keep this equation true, I have to make this a 2Y. So I again applied step 1 of the algorithm. And I repeat. I look at the leading term and I see if it's a multiple of this or of this. In this case it isn't, and so I need something else to do. And that's step 2, that's case 2, which is if not, then the point is that this 2y, you're not going to ever be able to cancel it using these other guys, and so you just give up and put that into R. So you take that term and you take it away from S and you put it into R because you're never going to be able to cancel it. So what you're left with is x times xy plus 1 minus x plus y plus 2y now goes into here. And now this guy disappears. When s equals 0, you're finished. So you repeat until s is equal to 0. And that's the algorithm, and it's very easy to see that this algorithm is correct. Give me just a second. So it's easy to see that the algorithm is correct because, f is bigger than each qi gi by definition, right? Because of the way that I constructed these qi's. And I need this condition that no monomial of r is a multiple of an initial monomial of gi. So that again is by definition, because all the things that I put into R are initial terms of S that are not multiples of any initial term of GS. And so really the way that you think of this is that you try to generalize what long division does, and this ends up being what long division spits out in this case. So what's your question, Andy?
I'm curious, are we subtracting just the initial term of S? I mean, in this case, it is the entire thing. Are we subtracting just the initial term, or are we subtracting the entire thing of S?
That's a good question. So we're only subtracting the initial term.
Okay.
And so it might happen that there were other things here in S, and that the algorithm might not finish yet.
Okay.
But in this case, it finishes. So are there any questions about the division algorithm? Yeah?
The second step, you decided to multiply x times xy plus 1. Could you have also used the second monomial?
Right, so my next question was, does something worry you about this division algorithm?
Not
And
unique.
the thing is that it's not unique. I made a choice here, because here I said, okay, remember I wanted to peel off x squared y, and so I said, is this guy a multiple of this guy or of this guy? And I kind of cared that it said yes, it's a multiple of xy, and so I put it into here. But I could have just as well said x squared y is a multiple of x, and instead of putting an x term here, I could have put an xy here. And that'll give me a completely different answer. And so that's the next remark that I was going to make, which is that if you pick a different order, you're going to get a different answer. So note the outcome say the answer depends entirely on the choices that you made along the way. So it definitely depends on the order less than, which is fine because that order was given to us as an input. But the thing is that it also depends on choices that we made. In step 1. Because in step 1 you might have different choices for I, and that might give you different answers. Okay? In fact, I was going to write another answer that you can get here, but maybe this is good if you guys practice with this. It's really good to do this by hand. So an exercise that I'll give to you, and maybe you can post the answer on the forum when you're done, is to do long division in a different way and get a different answer. Because I want you to see that it is possible to get a different answer. Okay. So that's the division algorithm. Any questions about it? Well,
And then F belongs to the ideal if there's no remainder, right?
so right, so that's the next thing that I was gonna say actually, which is that why should this be very worrisome to us? Well, because we were kind of after the answer to this question. We wanted to know, is F in the ideal generated by the GIs? And what we wanted to say is, well, if R is 0, then F is generated by the GIs. If R is not 0, then it's not. That's what we would imagine given what we know about the other case. But the problem here is that R is not unique, right? So it might be that you do this, and you get some answer for R, and it's not 0. But if you did it in a different way, you got R equals 0. And that should worry you, because that means that this is not really a bulletproof method for deciding this question. So this is why Grosvenor bases are so wonderful. Because the fact that the answer is not unique is a consequence of the fact that the GIs have been chosen randomly. But if we choose the GIs smartly, if we choose a Grosvenor basis, then we have nothing to worry about. So that's one of the really nice properties about Grosvenor basis. So that's a theorem. Say that we have a ring. We have our order, and we have a Grosvenor basis G1 up to Gn. Or then we have the following things. First of all, every polynomial in my ring can be written uniquely, and this is the key thing here, uniquely as some polynomial in the ideal plus some remainder, where so fi is in the ideal and no polynomial of R is a multiple of an initial term of one of the GIs. In other words, what I'm telling you is that the expression that you're going to get here is unique in the sense that this part is unique, this is the fi, and this part is unique, this is the R. So that's the first thing. The second thing is that the division algorithm will do this for us. Division algorithm does this independently of the order, independently of the choices. It's step one. And the third thing is that my polynomial f is in my ideal I if and only if this remainder that I get is 0. And so this is really my efficient way to test ideal membership. So this is ideal membership testing right here. You want to know whether a polynomial is in an ideal, then what you would do is cook up a Grosvenor basis, which you don't know how to do yet, but you will soon. But once you do the Grosvenor basis, then you just apply the division algorithm. You don't worry about whatever choices you're going to be making. You just check the polynomial R that you get in the end. If it's 0, F is in the ideal. If it's not 0, then F is not. This is a nice, important theorem about Grosvenor basis. And maybe the best thing about this theorem is that, yeah, question.
that word to the left of F and R in option A?
This word?
Yeah,
Every.
every. Okay.
Thank you. Any other ones? You get excited when I write that. And this is monomial. And this is multiple. Okay. The thing that I like about this theorem is that it's very easy. The statement is very long, and the proof fits in what I'm erasing right here. So proof. Part A. Existence. Well, I guess there is something more to say about the division algorithm, which is that it always terminates. You should always do this with any algorithm. And the reason why that's true is that every time you apply a step of the algorithm, the leading term is getting smaller and smaller and smaller. And it cannot get smaller indefinitely because of the well-ordering property. And so that's why this algorithm terminates. And so that means that existence, at least, is given by the division algorithm. The division algorithm is going to give you one way of doing this. So existence is okay by the division algorithm. What we need to prove is uniqueness. So let's suppose that we can write f in two ways. As fi plus r and as fi prime plus r. So then what I'm going to say is this. I'm going to say that I look at r minus r prime, and that is equal to fi prime minus fi, which means that it's in I. R minus r prime is a member of I. And that means that its initial term is in the ideal of initial term of I. Now, the thing is that I have a Gardner basis here, and that means that the initial ideal of I is generated by the initial term of these. Let's switch my letter. Let me switch back. I use K here, so let me use K here also. So this initial polynomial is generated by these guys. Now you might have looked at your homework already. I hope you did. And if you got to the last question already, the last question asks you to show the following: that if some polynomial is in this situation, it's generated by these monomials, then every one of the monomials here has to be a multiple of one of the monomials here. And I think that makes sense. Basically, you have a bunch of monomials, and monomials don't really mix. You can't really have cancellation between monomials. That's kind of the philosophy. And so if you have something that is generated by monomials, then every term of it has to be generated by monomials. In other words, what I'm saying is, this guy is a monomial. It's in the ideal generated by these monomials. The only way that's going to happen is if this guy is a multiple of one of these guys. And this is my homework 1, problem number 5. If you want to see a proof of this. That means that some one of these guys divides the initial term of r minus r prime. But if you think about this, this is already a contradiction, because I assumed that no monomial of r and no monomial of r prime is a multiple of an initial term of gi. But the initial term of r minus r prime has to come either from r or from not going to have this property. So this is a contradiction. What that shows is that actually r minus r prime is 0, and there's really no terms here. So that shows that my assumption that r was not equal to r prime is false. Really, r and r prime are the same, and therefore fi and f prime are also the same. So that proves part A, proves uniqueness. Now, part B, there's really nothing to say because we already know that the answer is unique, and if the division algorithm produces an answer, then it's got to be that unique answer. There's nothing to say there. Okay? I want to point something out to you. What I'm claiming is that fi is unique, but it might be that the qi's are different. But this is the guy that's unique. This guy is unique, and r is unique. Part C is also very easy because, especially this direction, is very easy. If r is equal to 0, then f equals fi plus 0, and fi is in I by definition. Okay. But the other direction is also very easy because if f is in the ideal, then I can write it as f plus 0, where f is in my ideal, and 0 has no monomial, blah, 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 blah. The point is that this is one of the expressions of that form. That expression is supposed to be unique, so this has to be on. That's it. So this is not a difficult theorem, but it's a very useful one. And like I said, this is really what computer algebra systems do. Alright, so that's one of the uses of Grosvenor bases, and we will discuss other ones, but I get a little bit nervous proving a lot of theorems about something that I don't know exists. So I think we should establish that these things exist before we spend weeks studying them. So let's prove that theorem. So Grosvenor bases always exist. What will be the next thing? So here's a nice proposition. Let's say that the conditions are always the same, by the way. I always say R is this, less than is this, I is an ideal. We start with the usual setup. So the first thing I would like to show is the following, that if you have polynomials g1 up to gk, I use k, right? In the ideal, and if they satisfy that the initial ideal of I is generated by the initial terms of these guys, then automatically you know that I is generated by Q1 up to I find this surprising, and I find this very useful, because you see I wrote my definition of Grosvenor bases over there, and so far, if we wanted to check that something is a Grosvenor basis, we had to check this and this, but what this proposition is telling me is that actually I could have just defined Grosvenor bases like this, because this statement implies this. So that'll be the first thing that we'll show, and after showing that, we will get the fact that I have a Grosvenor basis. that I is generated by these guys, we take some polynomial in F and we generate it. So we use the division algorithm and we get that F is equal to Q1 G1 plus etc. plus QK GK plus R. Okay? We don't know that this is unique because we don't know that this is a Grosvenor basis. But the thing is that this guy is in I and the GIs are in I. So that means that R is in I, which means that the initial term of R is among the initial terms of I, and this we know is generated by these guys. Okay? And so by the statement that I just made, this guy has to be a multiple of one of these. Some initial term of one of the GIs has to divide the initial term of R, but by the definition of R, this is not supposed to happen. That means that R must have no terms at all, and so R is equal to 0. This is a contradiction. So R is equal to 0, and therefore F is generated by GLs. So it's basically the same argument that I just made. Now for part B, I'm going to say the following. I'm going to say that the initial ideal is generated by the initial polynomials of all the polynomials in I. Okay? Now, I'm going to make a, I'm going to write a lemma here. And this lemma says the following. Let me put it this way. We have an ideal that has infinitely many generators. But we know that that's not the entire truth because we're in a land where every ideal is finally generated. Right? But we have infinitely many generators for them. We would like to say, well, out of these infinitely many guys, some finite subset generates. So that's true, but it takes a proof. So lemma, if you have a I is generated by the polynomials in some infinite set that we're going to call S, then we can find some subset which is finite and generates. So this is kind of a stronger version of this fact that not every ideal is finally generated. I think I'm not going to have time to give you the proof right now, but we can apply it here. We can say, okay, here we have an infinite generating set for this guy. That means that we can take a finite subset. For J subset of I, J finite. But what did I just do? I gave you a finite set of polynomials whose initial terms generate the initial ideal. And by part A, that's a Grosvenor basis. J is a that's the end of that proof. Well, that's the end of that proof, modulo this lemma, which you can see on the notes. The proof of this lemma is actually very simple, so I'll just let you read it in the notes. this is peace of mind. It's peace of mind because we know that governor spaces exist and we know that they're useful, so you're not necessarily wasting your time. Any questions?
So some of the students' heads were recorded. Is that okay with everybody? I want to get a permission. Okay, we recorded the permission then.